Well, good evening, ladies and gentlemen. I've got my podium. Welcome to the national headquarters of the Theosophical Society in America. My name is John Gianjosi. I'm the Director of Public Programs. And at this time, I ask that you turn off your cell phones, or at least silence them, or any other device that you may have. This evening's lecture is being streamed live, and I welcome people watching through the internet. The Theosophical Society promotes study, meditation, and service. We encourage open-minded inquiry into the world religions, philosophy, science, and the arts. And we have a deep respect for the unity of all life. Our goal is to help people explore the spiritual path so as to arrive at a deeper understanding regarding the wisdom of the ages. Furthermore, we feel this wisdom is not limited to any one tradition, and thus we offer programs from all traditions. I invite you to take one of our program brochures where you'll find the programs that we are offering during the spring-summer season that runs through until the end of August. These programs are also listed on our website, and there you have the opportunity to register for any of the programs that appeal to you. Now, the Theosophical Society is a membership organization, and there are benefits to being a member. However, what we offer here is open to the general public, all programs, all resources, and the beautiful grounds. People are always welcome to come and make use of these offerings. And we believe we are bringing something good into the world. These lecture series that we offer here every Thursday evening is an opportunity for us to hear presentations from different experts from different traditions and different fields. And this evening I'm very grateful that once again, it's the second occasion that Dr. William Wester has agreed to come and speak for us. Dr. Wester is a senior scientist at the Fermilab National Accelerator Laboratory, where he has conducted research on particle collisions and searched for possible new particles that make up the dark matter of the universe. He is also a member of the Dark Energy Survey Collaboration, where he studies the particle nature of the cosmos and the expanding universe using a very special telescope and scientific camera, which is situated in Chile. Now he's here for the second time this evening, and we are grateful, and this evening he will speak on Solving the Dark Matter Mystery, a search for the Axion particle. Please join me in welcoming Dr. William Wester.
Well, good evening. It's a delight to be back here and visit with you. And so first, let's take a look at this title, Solving the Dark Matter Mystery. Well, solving, so that's active tense, it's ongoing. It doesn't mean we'll have the solution necessarily by the end of this lecture, but we'll have to wait and see. And a search for the Axion particle. So in wanting to speak to you about the mystery of dark matter, this is the latest and greatest stuff, hot off the press stuff. I dare anybody to find on the internet another public lecture with a focus on the Axion puzzle, so the Axion particle. This is, you know, advanced second-year graduate school or something along those lines. But you're going to hear about the experiments that we've performed and actually get presented some of our latest results. So a few key things just to sort of put in the back of your mind as I begin. There's a scientific mystery of dark matter, and I'll describe that in some detail. This whole notion of particles and fields and force carriers, this is all around us. This is the universe as we know it scientifically. We live in a quantum universe where you can describe particles both as particles, or sometimes it's more convenient to describe the wave-like nature of a particle. And I'll you'll see some of that play out. But the main focus of this talk is, as an example of the dark matter mystery, I will describe the experimental details. I am an experimentalist, so I tried to make measurements. The experimental details searching for an axion. And what's exciting is that it's an experiment with discovery potential any day now, or perhaps it's going to be a struggle and nature will not be so kind and we'll have to be at work at it for 5 years or 10 years. And science is hard. It's really hard at this stage in our advancement in humanity to make large-scale progress in these mysteries, but that's what we're doing. And new clever ideas, both for my theoretical colleagues who might think of some new other way to solve some problem in our field, or some new way to do an experiment. Those clever ideas are also always needed. So this is a public lecture, but I am not apologizing. You will see equations, but there will be no test afterwards. And in studying science, my language is mathematics. So I'll describe and I'll point to a few things on the screen. This is my language of how to describe physics and the beauty of physics. And I want to share some of that with you, even though the trace of the gluonic stress energy tensor is not something you need to go home tonight and worry about. So I work at the Fermi National Accelerator Lab. It's a particle accelerator. So there are these large rings that particles can go traveling through to get to the very highest energies that we know about. And when we smash particles together, you know Einstein's famous equation. Who knows Einstein's famous equation? All together, E equals mc squared. Yeah, so at very high energy, energy and mass are somehow equivalent. And so we can produce some of the very new massive kinds of particles or study very rare processes because they're at a very high energy scale, and we can reach those energy scales by these giant complex machines. Sort of paradoxical, you know, to study the smallest scale stuff, you got to build these machines. So at Fermilab, we had this ring here, which was the Tevatron collider, where we collided particles in various locations around the ring. This is actually the larger ring. It's about 3.5 miles in circumference. This was an auxiliary ring to inject particles here, but we now use it as part of our complex to either send beams of particles down to experimental areas, or right now we are producing a beam of neutrino particles, and I'll tell you what a neutrino is, and they go right through the Earth, but we've built some enormous detectors that are now located in Minnesota, and with such a large detector, some of those neutrinos we can produce at Fermilab and capture them far away. And the next phase of this kind of work is to build a giant detector in South Dakota and deep in a mine. So for 25 years, we were the most powerful atom smasher, and now we produce the most neutrino beams, the most intense neutrino beams. And there are mysteries about neutrinos that Fermilab is going to be focused on. At the energy frontier now is our sister laboratory in Geneva, Switzerland, known as CERN. Instead of 2 TeV, its energy is much higher, 13 TeV. So it now collides particles with the very highest energy. And it also has a whole complex where a variety of particle physics experiments are conducted. So all this work in particle physics has led us to our understanding of all the fundamental particles in nature and all the forces of nature, and we call that the Standard Model. So if you remember your picture of the atom, you have a nucleus with electrons, then that nucleus was made up of protons and neutrons. Well, it turns out protons and neutrons are made up of smaller things called quarks. And they go by, funny names, up and down. Well, that's not so funny, but those are the names. But we now know that there are heavier versions, the charm quark, the strange quark, the bottom quark. And at Fermilab in the mid-1990s, we made a discovery. We discovered the top quark for the first time. Here's the electron. And just like the electron, there are heavier cousins, the muon, the tau, and associated with each of these is a different type of neutrino. And at Fermilab, we're trying to understand the different types of neutrinos because they can sort of change as they move from our laboratory getting produced as one type to where we detect them far away in either Minnesota or soon to be South Dakota. Along with the particles are the force carriers. There's the photon, the carrier of the electromagnetic force. So in our study of the quantum universe, sometimes it's convenient to not talk about a magnetic field or an electromagnetic wave, but to talk about the particle nature of light itself. And so the photon shows up. The gluon is responsible for what's called the strong nuclear force. And it's responsible for holding these quarks together in things like the proton or the neutron. Other kinds of forces, the W and Z, are known as the weak force carriers, and they're responsible for some forms of radioactive decay. And right here in the middle was a great celebration on July 4th, 2012. At 3 in the morning, I went over to Fermilab to the lecture hall, and just as we're simulcasting now, there was a simulcast from our sister laboratory at CERN where they announced the first conclusive evidence that they found this Higgs boson. Everywhere around us, everywhere in space, there's this Higgs field, and it somehow couples with all the particles and gives particles their mass. All massive particles are influenced by this Higgs field, which is everywhere. And that'll sound a little bit like some of this dark matters that I will talk about. So particles are all around us. Our everyday world, tables and water. You can look up water, H2O, hydrogen and oxygen, and we live in our everyday surroundings by the elements that make up the periodic table. But also, we live in a universe that has the particle nature around us everywhere. There are natural items that have some radioactive decay. A banana actually has a little bit of radioactivity. If you're radon gas in some of the basements, especially in the Midwest. So there's electrons and alpha particles and gamma radiation that's produced by nature. Neutrinos that we're studying at Fermilab are produced copiously in the sun, in the nuclear reactions in the sun. They're passing right through us all the time. They're very low energy, so they rarely, if ever, interact and pass right through the Earth. Again, unless you build a giant detector and try to capture some small number of them. Muons, that heavy cousin of the electron, that's in the cosmic radiation. In terms of fields and forces, we encounter electromagnetic fields. Similarly, we're standing on a planet and there's a gravitational field that holds us down. And a little bit hard to understand, but even this Higgs field is around us. And, it took scientists in particle physics 50 years to finally be able to detect it. So that's one of the great triumphs. Our best understanding of dark matter is that it also is something that is all around us. And by that I mean we're on the planet Earth, in a solar system, in a Milky Way galaxy. Our whole galaxy is filled up with this dark matter. and we do not have a clue as to what the dark matter is. So there's a new Star Wars movie coming out, and so there are two mysteries, Darth Matter and Darth Energy. The last time I was here, I focused on the dark energy problem, and that relates to how the universe is not only expanding, but accelerating in its expansion. But today I will focus on dark matter. So here's what is known as our cosmic pie chart. Our understanding from particle physics and particle astrophysics is 73% of the energy budget is this dark energy stuff. But if you just look at the matter, which is about a quarter of what's left, that whole chemistry chart, all the atoms that we know about, only comprise 5% or 4%. So all the heavy elements, less than 1%. All the mass and all the neutrinos in the universe, 0.3%. All the stars, just a fraction of a percent. Most of the mass in the universe of ordinary matter that we know about is hydrogen and helium gas that just happens to be out there in space. So, wow, we hardly know anything about the nature of all of matter. So dark matter has been around for some time as an idea. In fact, dark matter, you can trace this phrase back to the 1930s when a couple famous and infamous astronomers noticed that, hey, we're going to try to measure the mass of galaxies. And of course, the mass of galaxies should be related to how many stars or how bright the galaxy appears to be. And when they started to make measurements to determine what the mass is, they got nowhere close to the right answer and said there just has to be missing matter. Now at this time it might have been all the hydrogen and helium gas because they didn't have a full accounting. But one of the great heroines of science, Vera Rubin, and many people say she's a strong candidate for a Nobel Prize, she earned her way by making very careful and precise measurements from astronomical observations of stars, sort of the stars way on the outer reaches of our galaxy or of a neighboring galaxy like Andromeda. See, if this is our galaxy, if all the mass were contained in the big dense star pile right here at the origin, as you moved out farther away from the center of the galaxy, you're getting farther and farther away from that big clump of mass. And you would expect the speed at which a star would go around the galaxy to start to fall off as it feels less and less influence. I mean, this is, freshman year physics. So it's, that would be the effect. And to her surprise and to her credit, she determined that instead these very outer stars had a velocity that more or less became kind of flat. And if you had matter everywhere, a halo of matter around that galaxy, that is what you would expect from these rotation curves. And so that put dark matter on a much firmer scientific footing. And since then, not only on the galaxy scale, but you can try to map galaxies that have formed giant clusters of galaxies between where the location of those galaxies in that galaxy cluster is and where the dark matter is. Here are two colliding clusters of galaxies. Excuse me. Most of the hydrogen and helium is here in the middle, but you can determine from the gravitational effects that most of the matter is in these bluish false color representations. And then finally, there's some beautiful work looking at the earliest photons from the universe. The temperature of the universe is like 4 degrees Kelvin, almost completely uniform. But at maybe 10 parts per million, there are tiny fluctuations in that temperature. And those are shown in these blue and red splotches here. And if you look at how those fill up the entire sky, you get a very peaky set of data. And a very simple model explains this very detailed graph with all these peaks. And one of those parameters is how much matter there is in the universe. And so we can get that very precise 24% of the energy budget of the universe is dark matter from these observations. But the question is, what is the dark matter? What is, 5 times of ordinary matter is dark matter? What is it? Well, here's a plot from a theorist who liked to, show everything. There are all these nice little boxes of new theoretical possibilities about where the dark matter is. There's a scientist down at the University of Chicago who says, maybe you shouldn't be so rigid in, labeling all the dark matter in terms of its mass and how strongly it couples with ordinary matter. So he just drew his uncertainty as the dark matter moose. And so we don't know, if we should be searching in this hoof here or these antlers, but somewhere is the solution to what is the particle nature of dark matter. So here's an example dark matter search that we did at Fermilab. Suppose dark matter can interact with photons, particles of light. And so what we did is we took a light and we shone it into an accelerator magnet. We have high strength magnets at Fermilab. And maybe that interaction between the laser photon and the magnetic field photon would produce a dark matter candidate. And now we had to think of a way to detect it. And so there's a class of experiments called a light shining through a wall experiment. And it goes like this. In fact, it was done in the early 1990s. Somebody took an accelerator magnet and another accelerator magnet. They shone a light in. And if some of the photons converted to dark matter particles, they would be able to escape right out of this vacuum system, go through a wall, because dark matter doesn't interact with ordinary matter at any high level. And then in this other magnet, there would be a small probability of converting back into a photon, back into a particle of light that a photomultiplier tube could then detect. So yes, at Fermilab, that's what we do. We sit around trying to look for things emerging from the wall, but you do have to explain it not only to your immediate boss, but to the funding agency that we're grateful for support. So in 1992, this was the result that they had. Here is the possible dark matter mass in units of electron volts, so energy, E equals mc squared, so you can convert that back to your favorite mass unit. And essentially the strength of how strongly it coupled to ordinary matter. And here it's in units of inverse GeV. We like energy units. I remind you, 10 to the third is a TeV, so this is where the tevatron is, and about a factor of 10 more, this is where the LHC was. So just this simple experiment was going many factors in higher energy reach than the LHC, but only for this one possible rare process. And what you see in this hashed region, the mass and the coupling region, that they completely excluded. They did not see any light shining through a wall. And if the dark matter particle was at this mass or had a very strong coupling to the photon, they would have seen it And since they didn't, they could exclude that region. Well, in 2006, some researchers came along and did another laser experiment. Now, one thing I'll call your attention to is it's like the laser photon oscillating into a dark matter particle. And so you see at some point the oscillation features come into play. And where there's like no sensitivity, that's just determined by the random choice of magnets, spare magnets that they found and set up their apparatus with, and the parameters of the magnetic field and whatnot. And so in 2006, an experiment in Europe reported a positive signal that, if interpreted as a dark matter particle, would have lived right in one of these regions where there was no sensitivity. And there happened to be no sensitivity just because that's what the size magnets they had lying around when they did this experiment. These guys might have been the most unlucky group of scientists ever. But we said, okay, it's a bit of a long shot, but there was a real result that needed to be checked scientifically, and that's what we do. They published all their data. They looked and said, hey, we don't really understand where this signal's coming from, but it should show up in a light shining through a wall experiment. And here was our apparatus. We had our laser inside a laser-safe box. Here is a Tevatron dipole magnet, about 6 meters in length. So this generated our high field. Now, instead of using 2 magnets, we put our blocker, our wall, either in the middle, or the little bit of cleverness that we had is we had it mounted onto what we called our plunger, and we could move the wall closer to one end of the magnet if we so chose. And then here was our photomultiplier tube. So if something converted into dark matter went through our wall, we would detect any reconverted photons with this device. Well, here is actual data that we took, and a photomultiplier tube has sort of a constant background level. And if I look at a 100 nanosecond time scale, so very brief, yeah, there's a little bit of background, but not much. One part of our experiment was to let some of our laser photons through by essentially drilling a hole through the wall. And this is what those photons looked like. They arrived at our photomultiplier tube exactly as expected at the speed of light distance from the laser to our phototube. And so we have these dashed lines where we could look to see if we saw any regenerated photons. Well, we either saw 1, 0, 1, or 2, depending on how we configured our apparatus. And you can see that those are very consistent with our background levels. So we essentially had no detection of this light shining through a wall. And when we put in the power of our experiment, instead of excluding this tan region, we excluded everything above the dark lines. And because we could move our wall not only in the middle but towards one end, we could fill in these regions where the other experiment had no sensitivity. And we essentially ruled out the particle interpretation of that experiment in Europe. So what's been sort of satisfying is that people still do these experiments, but in sort of the 10 years since we've published our data, they've maybe gotten a factor of 5 or so more sensitive, but not much more than that. It's very hard to, once you have some background, to gain much in sensitivity. So the particle we were searching for was an Axion-like particle, a dark matter candidate that is very similar to the Axion in that it couples to 2 photons. But the actual particle called the Axion arises from a deeper level of initial understanding, and we have to go back to that strong force, one of the four fundamental forces in particle physics. Now here's that nice math equation with the trace of the gluon stress energy tensor. But what I want to call your attention to is that there's a term in our theory of the strong interaction that has an angle in it. And an angle could be any number from 0 to 360 degrees, or because we like math, any angle between 0 and 2 pi. 2 pi is 360 degrees. And people have tried to measure this as one of the fundamental parameters of the standard model. And to their surprise, this effective angle is vanishingly small. We know it has to be less than 10 to the minus 10. So if you pick a random number from 0 to 360 and you pull out 10 to the minus 10, that's a pretty strange result. Maybe there's some reason why this number is vanishingly small. And so a number of very famous theorists, say, hey, the solutions is going to be something that I'll describe as the axion. And, how do you solve this strong CP problem in our theory of particle physics? So the measurement of this has to be less than 10 to the minus 10 comes from scientists studying the neutron. And as a function of year, they try to measure some property called the electric dipole moment of the neutron. It's essentially like, hey, if you have up and down quarks, is there any net direction to the charge that are contained in these quarks? And the theory says it should be about 10 to the minus 16 times this angle. Well, if this angle is 10 to the minus 10, now we're at the, 10 to the minus 25 or 26. So our current measurements, not seeing any electric dipole moment, is a direct measurement of this angle, and this shows how we get something that we know scientifically to be vanishingly small. So the axion was invented theoretically to clean up the strong CP problem of particle physics. And Roberto Pesce and another great woman physicist who's at Stanford, at SLAC, Helen Quinn, invented the mechanism by which you could solve this problem. And shortly thereafter, these two guys realized that if that solution was correct, there would be a new particle called the axion. And so, again, clean up the strong CP problem, and indeed it was named Axion after a popular detergent in the late 70s. So the basic idea, and I'm going to show you some slides that I've also used in a scientific presentation, but it gives you an idea of how some properties of this solution can give rise to an axion particle. So in theoretical physics, in axions, we talk about the axions having high energy states, high up on the axis, and low energy states. And there was some symmetry of nature that when it got broken, it kind of tipped this, this wine bottle potential shape. And once this wine bottle potential shape got tipped, there's a natural spot that's at very low energy. And so the reason why that angle is vanishingly small is because the particle physics found this ultra low energy spot. And that's why it's small. Now, a closer examination down here at the bottom, excuse me, your particle can kind of go back and forth at the very bottom and oscillate back and forth. Well, oscillating in energy is effectively a mass. And so this same theory gives rise to an understanding of why this axion particle, if it exists, would be very light in its mass. And the third thing is in the tipping of this wine bottle potential, you go from a high energy state down to this lower energy state. And if you're doing that over all the universe, that explains all that energy being converted into dark matter mass. So this one theory, this elegant theory, explains the strong CP problem. It explains why there's so much dark matter around, and it even says something that the particle should be at some very low mass value. So let's go try to find it. So here is the axion, and theoretically it couples to 2 photons, and it should have a mass related to, below an electron volt, but much lower because the energy scales are like 10 to the 10 GeV. And remember, this is many orders of magnitude more energetic than even our CERN collider, or there's even some higher energy scale involved. So that really keeps the mass very low. And so we look, here is the mass of the axion, and it goes from 10 to the minus 6, a micro electron volt, up to roughly a milli electron volt. And here's how strongly it couples to ordinary matter. Remember the 10 to the minus 10 and 10 to the minus 12 are, so this is GeV, so 10 to the minus 3 GeV is the tevatron, and a factor of 10 more is CERN. So that's way up here. So we're looking at very weak couplings to ordinary matter. And what do we already know? Well, we know things like if the axion were way too light, that tipping of that potential would produce too much dark matter. So we know it really should be above 10 to the minus 6. In 1987, there was a supernova explosion, and we saw how much energy got released in a nearby supernova. And if the energy was also being released by axions, we would have seen some effects. And that kind of says, okay, you kind of have to be less than 10 to the minus 3 electron volts. Finally, if you couple to ordinary matter very strongly, like 10 to the minus 10 or better, we know, for instance, the sun shines. Well, if the sun were just releasing its energy in light and in neutrinos, okay, that's fine. But if the sun were also emitting axions, because you have magnetic fields in the sun and lots of photons in the sun would burn out in 1,000 years. And since experimentally we seem to be okay with that limit, we know that the axion has to have a weaker coupling than 10 to the minus 10. Finally, when you take, that wine bottle potential into account, how it couples to photons, there's this diagonal band where the axion should live, and it has some width to it because there are different theoretical models in detail, but it's a pretty narrow band. But this essentially gives us a theoretical target to try to build experiments to search for the dark matter axion. Now, there's another favorite candidate for dark matter called weakly interacting massive particles. They have nothing to do with, with the axion, but it's another class, and it's also based upon a highly motivated theory. Essentially, that theory says for every particle that we know about, there's a supersymmetric particle that we haven't found yet. Well, for a while, I really liked that theory. It kind of said I was only halfway done in my field of particle physics. And so that was a possibility. And this is an active area of research. both at the Tevatron and at CERN, they're trying to produce these massive particles at colliders. If they're dark matter and all around us and passing through us, if you build a detector very sensitive underground, you might see some interactions. Or you can look in space with telescopes and see if these dark matter particles are annihilating. Well, I'll just give you the result from our search when I worked on the Tevatron Collider project. A great triumph of science, building this complicated accelerator, building this complicated detector. Now we're sensitive to dark matter, very exciting. We're covered in the New York Times, and the headline reads, 315 physicists report failure in the search of supersymmetry. We all kind of hugged, our heads down low. I mean, come on, it was a great search, and we did discover the top quark. So that this is big science. We don't know the nature of nature, and so we have to explore. And so now we have colleagues at CERN in Geneva, Switzerland. So dark matter continues to be elusive. And so some people are betting on WIMPs. And so, they hope that some WIMP comes in and here's a nucleus. And, as our solar system, our sun and our Earth going around, moves in our Milky Way galaxy, all that dark matter around it, we're just passing through. I kind of said the dark matter coming in, but the proper picture is there's this halo of dark matter, and our whole solar system is moving in our galaxy, and so we're just sort of plowing through this cloud of dark matter, and maybe a very sensitive detector will see some very low energy scatter and enough of it above background to maybe the WIMP hypothesis is correct. Or maybe it's an axion. And so the way I think of an axion is when you get down to our detector level, you have this giant football stadium-sized cloud of axions at one time moving through our detectors, and it only intersects a small part of our detector, but all these axions are behaving in the same way, and they might leave some signal in our apparatus. And I'll tell you how we search for axions. So here is the small group of us on the Axion Dark Matter Experiment. This is right now being conducted at the University of Washington. And so these are about 2/3 of our collaboration members. That's me there, and you see we have a couple women scientists and some older scientists and some younger scientists. So it's a very nice group to work with. We are doing what is called a Axion haloscope, the dark matter halo that surrounds everything. And so here is our cloud of axions, and what we hope is in a very high magnetic field, in a microwave cavity, an axion can come in, interact with the magnetic field, and essentially excite a detectable photon that is essentially read out by RF electronics, the same electronics in your cell phones and things, except we have to have almost zero noise. But eventually we hope to see a signal that is indicative of dark matter axions in this apparatus. It's all about signal to noise. So we get higher signal if we use a higher magnetic field, if we have a bigger volume to capture more of that football-sized field. And then that microwave cavity has a special purpose. It could help amplify the signal that we're searching for. So if the cavity is at the same frequency of the axion, or the frequency corresponding to the axion mass, we get a very large enhancement. In the end, we are trying to detect 10 to the minus 23rd watts of power. You know, a light bulb is, 40 watts. So 10 to the minus 23, it's an incredibly challenging effort to do this. And so this is the apparatus. This is our haloscope. What it is, it's a tall cylinder. Here's our microwave cavity. It fits down in the ground where there's a very high magnetic field. And what we have in our cavity are these rods that can tune the frequency at which the cavity is most sensitive to. And so what you're going to see is that we move these tuning rods to try to scan the right frequency that corresponds to the dark matter axion. And then we have superconducting quantum interference device detectors, essentially the most sensitive detector that you can imagine that can receive such a small power signal, and you could be sure that you've observed that. So again, sort of from the side, here's that cylinder. Here's where the 8 Tesla magnet in the cavity sits. We are below 1 Kelvin in temperature. We got to keep the noise way down so any thermal vibrations would swamp our signal. We put our amplifier up here in this region, and we have to cancel this very high magnetic field so as our amplifier is not disturbed. And you can see some frost from the cryogenics that are used. And so this just shows the cavities. When the tuning rod is in one position, we are most sensitive to one frequency, and if we move the tuning rod, we would be sensitive to a different frequency, a different axion mass in our search for where the axion might be. And it gets even more complicated. The axion only couples to certain resonant modes in the cavity, and sometimes they interfere with each other, and so we have to take care of all that detail as well. So let me move to a demonstration. So if you could turn the microphone on. Can you turn that on?
It's on.
Is it on? Yes, it is. Okay. So remember, the axion is something that's oscillating, just like the note from a tuning fork. Now, what the axion couples to our detector very weakly. And so, let me just, I think this is okay with the sound. So very weakly. So,
Do you have to take that little thing off?
I will. Yep. So the vibrations and the tone that you hear is just a little bit of air pressure moving back and forth at the frequency of this tuning fork. Well, you don't really get if you're a hot summer day and it's kind of hot in here, you don't really get much relief by just having a little air pressure vibrate back and forth. This is supposed to represent, this other apparatus is supposed to represent our detector. And if our axion is making noise as we pass through the dark matter field, if I turn off the axion noisemaker, we should listen for the axion to be picked up by our apparatus here. And so let me make the axions. Anybody hear anything? You heard a little bit? Well, maybe a little bit, maybe not so much, because this tuning rod had a different frequency, through this device. But if I tune this apparatus to the same frequency as our axion signal, we'll see if we can be better at transmitting power from the axion through the air, very weakly coupled, into our apparatus. It's still going. In fact, if you put your finger on there, you can feel it vibrating. So that's the same concept that we're trying to do with these radio frequency waves in our electronics and using our microwave cavity to amplify the signal that we might see. And so we take data. So we put our tuning rods at a certain frequency and we take some data. Here's a spectrum, another spectrum. We move the frequency a little bit and march along. And to show you what a signal might look like, we can synthetically inject either that very strong theoretical model or the weak theoretical model. You'd be hard-pressed to try to pick out a little peak here, but if you sum up all the data that we take at that particular frequency, we would be sensitive to that very weak Axion signal. It's going to be so much fun if any day now in our search the Axion shows up. Because once it shows up, we know that magic frequency. That apparatus is not so hard once you know the key frequency, the key mass parameter. And what's exciting is after we're convinced, and it's going to take a little while to convince ourselves, but we can go into doing Axion astronomy the next day. We can really look to see is the shape of the Axion signal consistent with us moving through the halo of dark matter. We can look for tiny effects, because if it is just the Earth moving around the sun and the sun rotating around each day would kind of shift that peak just a little bit each time we do that. So not only is our experiment one to search for the Axion, but it might be the first experiment to begin some new way to look at the universe. So here's our famous plot again, the mass and the coupling to matter. And so what we propose to our funding agency, here is the sort of the trapezoid, that's the preferred region for the Axion that solves the strong CP problem, that accounts for the dark matter of the universe. And the plan is to march up from where we are right now to higher and higher frequencies. And, theoretically, it should be from a few micro electron volts, maybe up to 100 micro electron volts. We're probing, at 600 megahertz or a gigahertz, and maybe we need to go up to 10, 20, 40 gigahertz. And so that defines our search region. And so where we are right now is just looking at the very first frequency range. And what's exciting is for the first time in history, previously we've gotten down and just barely touched this top line, but essentially lowering all of our temperatures, taking all the care with our high magnetic field, taking care of those quantum interference devices, we can now probe down below this lower line and conclusively search for this Axion particle. And so just a few weeks ago, our first results in this effort were published in Physical Review Letters. I think this is the fourth public time that these results have ever been shown. And it's exciting to report that indeed we are below this lower theoretical line. Right now, over this very narrow frequency and mass range, but we've been taking data for about a year after this initial collection, and any day now, as we continue to march up in mass, we might be sensitive to the Axion. So our current setup gets us up to maybe 1.5 gigahertz. At higher frequencies, the higher the frequency, the smaller the cavity has to be, but you want to have the volume as well. So we've already built prototype small cavities and figured out how we might put 4 of them together. That would take us up to 2 gigahertz. Maybe we would need 14 small cavities, and there's some technology that we're working on and doing R&D for to get up to 4 gigahertz, and even beyond 10 gigahertz, we're starting to think of new ideas. What we essentially have to do is defeat quantum mechanics. There's a noise level associated with any temperature, and we have to essentially detect photons without destroying them. And some of the new technologies in quantum computing would allow for that to take place. It doesn't violate quantum mechanics. It puts all the uncertainty where you don't care about it, but it makes it uncertain and makes it very precise whether or not you've generated a new photon in your cavity or not. And so this is now in the R&D phase, just getting started, including at places like Fermilab, where we have magnets, superconducting cavity, and all that kind of infrastructure. So this is the current state of theory. We don't know what dark matter is. We shouldn't forget that. I told you the story of the Axion, a very highly motivated candidate. We're searching for it. It's discovery science. Any day it could happen, but maybe nature is not so kind, and we either live in some other little theoretical idea, or we need some clever experiment. And there are clever experimental ideas all over the world as people think about new ways to detect possible dark matter. Why haven't we seen it so far? What could it still be? We're trying to tackle this problem from a variety of different directions. And essentially, cover the whole gamut of what the dark matter mass might be and all these different techniques. So the nature of dark matter is a current mystery, both theory and experiment. We don't know what it is. We don't know how to measure it. A strong candidate is this Axion, which solves some fundamental problems that we do know about. And I'm on an exciting experiment where every day we continue to scan in frequency space. Maybe the Axion has a mass just around the corner, or it might take several years of scanning, and we might even have to get up above 10 gigahertz and use some new technology that we're developing now. Science continues to advance, and hopefully dark matter and dark energy will be better understood. And it just might take some crazy idea somewhere along the lines. Maybe light shining through walls might be the right thing to do after all. So thank you.
Thank you so much, William. We do have time for questions, so please just raise your hand and I'll bring you the microphone.
I saw that you did experiments to exclude the very first experiments where you excluded a region, but that region was already excluded with cosmic. Was that not known at the time, or did you do it as an experiment?
Yeah. So when that result from Europe came out and said that there's a possible chance we've seen a very strongly coupled dark matter candidate that would have otherwise been excluded, like the sun doesn't burn out in 1,000 years. Within the next week, there were about 15 new theoretical papers published by my clever theoretical colleagues who thought of new ways to evade that bound. And so we think that's a pretty robust bound. We never talk in absolute terms in science, but it looks robust. Everything we know about it is robust, but maybe there is one of those crazy ideas still gives some wiggle room out of the picture I've painted.
William, I've got a question from somebody who wrote it in. It's kind of complicated. I'll do my best with the names. Tom Van Flandern supported Les Sages' discredited theory of push gravitation, Do you believe that Lesage's, I don't know if that's correct, theory deserves to be discredited? And if so, why? And by the way, Van Flandern maintained that gravity propagates faster than the speed of light.
Yeah. So I paid homage to theoretical ideas that span the gamut. And, you know, I'm very open to such ideas. We do have a scientific publication process and review process, and some scientists, you know, feel their theories have not received adequate attention. That's part of the scientific process as we know it. There are venues for works to be published without the same kind of peer review, and it's a matter of time whether or not a particular theory regains some focus. You know, there have been many theories discarded at one time that then after time you get a new look at that theory and say, ah, maybe. Or, you know, the other question is there are a lot of theories that as an experimentalist I do not know how to test yet. So for instance, string theory. You know, maybe there's something associated with vibrating strings even below the quark level, and maybe even electrons are related to vibrating strings or loops and things like that. Well, I don't know, for those theories, the energy scales are so high, I don't know how to make an experiment yet to test those. So even something that mathematically has a beautiful foundation like string theory, it may be part of our universe, but I'm an experimentalist and I'd like to verify that. And it may take a clever idea. You know, we've done a couple quantum measurements at Fermilab using some novel ideas. Do they touch string theory or not? You know, was this idea that was the person watching rose? You know, I'm open to these things, but it's a process. It's a scientific process that we're on, and hopefully someday humanity will narrow into the right thing.
Thank you.
One term that you used a number of times was coupling.
Yeah.
And I'd like to understand better what it would mean for dark matter to couple with ordinary matter, and also why would we expect dark matter to couple with ordinary matter when it seems to exist in a different realm that we're having trouble penetrating? Why would we assume that they're going to couple in some way?
Yeah, that's an excellent question. And so by coupling, I essentially mean that there's some force between ordinary matter and dark matter. Just like there's a coupling between, let's say, two electrons that have the same charge. They're going to feel the electromagnetic force. There's going to be a coupling between those two electrons that essentially gives rise to the force that will cause those electrons to move away from each other. So far, the only thing we know that dark matter couples to is gravity, because we can make direct observations through our telescopes. I described a number of them, where we see the effects of all that matter essentially warping the space-time so light gets bent in funny ways, or you see some of the effects that I showed for evidence for dark matter. The answer is we do not know. There could be a zero connection between the dark universe and our ordinary universe. In the case of the theories of supersymmetry or the axion, there are those natural connections. So in supersymmetry, we would expect to see some signatures in our particle collisions that would indicate the existence of these weakly interacting massive particles. The theory of the axion naturally builds in this coupling to two photons, and once you know that exists, you have a scheme of searching for it. So again, in terms of an absolute sense, there are ways to evade us ever being able to detect dark matter except through gravitational effects, but we continue to search.
There was one other question from that somebody sent in. As you work at Fermilab, do the scientists there ever discuss the Fermi paradox?
Enrico Fermi was certainly a founding father of modern physics and nuclear physics. I'd have to see exactly what formulation of the paradox is being spoken, so I don't want to step out there. But yeah, one of the favorite things at Fermilab in its cafeteria, not so much anymore, but you used to go around and look at the napkins, most of which were scribbled with equations and ideas and things like that. So yes, indeed, we do have quite lively discussions.
Since we only know, okay, when we only know what a tiny little part of a universe is made of, 4%, that 4% is made out of particles. Do we assume that dark matter is made out of particles because we just know that that's the only thing we know, or is there any other theories, maybe with a continuum, or is there other theories that are, let's say, commonly held feasible that are not WIMPs and not axions?
Yeah, there are a number of theories, and that last set of a whole class of experiments, there are some models that say ultralight particles might be involved, and so there's some new experiments to try to lower the energies and to be sensitive to even a lighter class of particles. But so far there aren't any other, there are, somebody drew a diagram, there are elegant theories and there are testable theories. The elegant and testable theories are the WIMP searches and the axions. How far you move into either elegance or testability is a matter of choice, and when we make proposals, it's also a matter of cost and convincing our funding agencies that we have a reasonable chance of success.
So from an experimental point of view, that makes total sense, but from a theoretical point of view, are people thinking outside of particle theories?
Yeah, in fact, that experiment in 2006 from Europe, which we disproved, really started a lot of people thinking outside the box. And since much of our measurements of standard model are in agreement, since we've completed the standard model picture with the Higgs boson, I mean, there's very exciting times coming ahead at our sister laboratory at CERN, as they now collect more data than has ever been collected to see if everything fits together as, when you start making precise measurements. That really tests the theory in a strong way. But we're also beginning to think, are there some things that we might have overlooked? One theory is a dark photon, that most of the dark matter is in an ordinary photon, except it's dark. You can't really build a detector to see it. And maybe some of our ordinary photons oscillate into these dark photons. And so you can set up an experiment to test that. And that theory is pretty close to being elegant and testable, because you can sort of get the right amount of dark matter in the universe with a theory like that. Just before that, I think the Fermi paradox was essentially, a statement by Fermi on the existence of intelligent life, and why don't we see where is all the intelligent life if it's out there? And That's I have to turn my brain just a little bit outside of the ordinary thoughts, and of course we discuss these things, and of course we're paying attention to, the fact that there are many observations of new planets around distant stars. It's amazing we can determine that. Soon we'll be able to determine the atmospheres around some of those planets. And we can look at the complexity of life here on our own planet and extrapolate. So it's an exciting time from that point of view as well. Whether or not there's a scientific way to demonstrate for sure that there's intelligent life out there, that continues to be the paradox. So,
thank you. I have a question here.
So Dr. Wester, this is very nuts and bolts and boring, but looking at some of the mathematical formulae up on your board, you had noted CP and CM. What do those stand for?
Yeah. So CP is a symmetry of nature. It essentially says, what does the theory look like if you change from a particle to an antiparticle and then look at some reaction with its mirror image? So you put those two combinations together, do you get the same thing or not? And so that's a fundamental theory. We know that CP, this symmetry of nature, is violated in interactions that involve the weak force, those W and Z particles. But the strong force seems to conserve CP, and that's the fundamental symmetry that we're testing through that measurement of the dipole moment of the neutron. CDM might have been the other abbreviation, and that stands for cold dark matter. One thing we sort of know is that dark matter doesn't appear to be, there is some region where it could be a neutrino-like particle but it would have warm properties. And as far as we see, most of our observations sort of suggest that the dark matter is not adding new relativistic particles to the equation. So
that actually leads up to my question. I was interested in knowing how sublimation affects looking for these particles.
So sublimation is many of these aspects we invoke the properties of we call it thermodynamics. So properties of temperature and heat and looking at the conditions of the very early universe. And as the universe, expanded in some big bang, where did the particles of dark matter emerge? Where was this symmetry breaking for the axions? Was it before the period of rapid inflation, rapid expansion of the universe, or was it after? And so, without being specific, all these kinds of concepts definitely come into play in the theoretical ideas of new particles.
Are we done with the questions then? Looks like we're done with the questions. Thank you so much, Doctor. And I'd just like to make a couple of announcements before I invite you to have refreshments. And because this is a long weekend, we're not having any programs on Saturday or Sunday or Monday, and we can all stay home and enjoy ourselves, or go on vacation and enjoy ourselves. Or you can come here and enjoy yourself in the on the grounds. I'll probably do that. But Thursday next week, we're going to have Bhikkhuni Vimala. She's an ordained Buddhist nun in the Theravada tradition. And she will be speaking on the Buddha's essential teachings. And then on the Saturday, on the following week, that Saturday she's leading a day-long meditation workshop. So that'll be Saturday, June the 2nd. And the theme of the workshop will be Exploring the Four Noble Truths. Sister Vimala has spoken here on numerous occasions and also led these at least one-day retreats, and they've always been very well received, and most people seem to enjoy them greatly. And I invite you to come for the lecture next week, and if you are interested in meditation, deepening your meditation, or learning more about the meditation practice from the Buddhist tradition, consider registering for that workshop. And you can do so online. Thank you all for coming this evening. Thank you, Dr. Wester. Please stay and have some refreshments.